burn out if it gets sucked away. Now, if it doesn't get sucked away, it sits there and collects water from the atmosphere, puts more water in your gas tank. But, you know, wintertime, that doesn't happen very often. Summertime, that's an issue. Anyway, I digress again. So, the last, let's see here. Okay, so now what I want to talk about is the second type of intermolecular bond, and that is best shown with acetone. So let's take a look at acetone. Here is acetone right here. Now this is one molecule of acetone right here. This is a carbon with 3 hydrogens, both bonding to a single carbon that is double bonded to an oxygen. Now, the dipole moment that you see here is pulling the electrons towards that oxygen, making this side negative and this whole side here positive. Now, what's different about this than the last scenario we dealt with ethanol and methanol, as it turns out, is that there's a hydrogen bonding to that oxygen. So we call those hydrogen bonds. When you have hydrogen and oxygen and the bonding's taking place like we saw between the water and the ethanol, that is called hydrogen bonding. That is the strongest of all the intermolecular bonding for compounds, molecules, covalent molecules particularly. Well, that's the only thing there is. So what we see here is the attraction of the negative part of the acetone with the positive part of the other acetone, and there is that connection being made here. The difference here is that there is no hydrogen involved. And when you pull electrons away from hydrogen, it makes that very positive. This is just an out-and-out slight difference here. You've got all these things over here shooting at. So this is not nearly the strong bond that takes place with ethanol and water or methanol and water. So we don't call this hydrogen bonding because there's no hydrogen. But these things are polar. It's got a negative side and a positive side. So we call this, to me it sounds redundant, but the name of it is dipole-dipole bond. I think it's the dumbest name in the history of chemistry, but that is what we're stuck with. Okay? So a dipole-dipole bond is a bond for a polar molecule bonding to a polar molecule of which both of the molecules do not have hydrogen on an electronegative element. So the oxygen 1 acetone is attracted to the bulky carbon of another acetone, making it not as strong an intermolecular bond as the hydrogen bond in ethanol. This molecular bond is known as dipole-dipole bond. So it comes from the land of silly people who come up with names. The third type of bond deals with non-polar molecules. And this is really interesting stuff, at least for someone like me. The last of the intermolecular bonds deal with non-polar molecules bonding to other non-polar molecules or to non-polar portions of polar molecules. In other words, you have a non-polar molecule and a non-polar molecule that like dissolves like. That means they will find a way to bond to each other. And I'll describe how that works. But you can have a really big, honking polar molecule where the polarity is on one side and this long portion or big portion over here that is non-polar, so other non-polar molecules will bond to that portion and stay away from the polar part. That's very common, particularly when we deal with detergents, soaps. That kind of idea works great because the non-polar part of laundry soap will bond to the grease because grease is non-polar, and the polar part of the laundry soap will bond to dirt and anything that turns out to be polar. So that's the theory behind laundry. And there's other great stuff about that, but we'll talk about that later on. So, take the bonding of benzene to naphthalene. Benzene is C6H6. No other element on the carbon except hydrogen. That makes it nonpolar. Naphthalene, same thing, C10H8. Tons of carbon with hydrogens all around it, making it non-polar. Neither molecule is a positive side or a negative side because of the equal distribution of electrons around the molecule. So how in the world are they going to bond to each other if they don't have a positive or negative side? Well, it turns out we actually kind of do have a positive and negative side. Just a little bit. Just enough where they can actually form a quick bond. Right? What one forgets about electrons is that they are not static. They don't stand still and say, oh, I'm here stuck in this atom bored out. No! They are moving constantly. In fact, they're moving so fast that they approach the speed of light. The motion is also random and reactionary to the position of the other electrons since they do not like being next to each other. Why? Because they're all negative. Like charges repel. Many times there is an overabundance of electrons on one side of the molecule for an extremely brief moment in time. That makes that side negative and the other side positive in relative terms. Because of that overload on two neighboring molecules, they will momentarily be attracted to each other at the point of those two molecules, only to separate just as quickly when the electrons come back. So what are you doing? Get out of here. Gone. And as soon as they turn their backs, they're leaving, and they're back together again. This is back and forth, back and forth, back and forth motion. Constantly, and the larger the molecules, the more places they're going to have these, weird distributions of electrons creating these bonds. A gecko walks on walls and ceilings using van der Waals forces. That's the name of these bonds. These are van der Waals forces, named after Dutch scientists and founders. They are able somehow, this is amazing, are able to move their electrons around on their feet. They don't have sticky pads. We had a pet gecko for about a year. It was smooth, almost ragged feet, but it could crawl up walls or ceilings if it wanted to. We made sure it didn't do that, but by manipulating the electrons and creating these van der Waals forces with the walls and the ceiling. That's how they do that. It's one of nature's gifts to those people, to those creatures, but they really don't care. They just want to walk, not think about it. They can't think about it. You got to bring about the size of a BB shell. Anyway, this constant changes of the electronic terrain around the molecule creates what some scientists call a force rather than a bond. Hence, the name of the bond is van der Waals Forces, named after the Dutch scientists who found it. Bottom line, all right, so this is the whole reason why we're going through this. The three intermolecular forces in order of strength from strongest to weakest are hydrogen bonds, dipole-dipole bonds, and van der Waals forces, which are also sometimes known as London dispersion forces. Your goal is to figure out what intermolecular forces are holding identical molecules together in non-gaseous states. Now, gases won't bond together. These are all liquids and solids. Example, what is the polarity of CH3OCH2CH3, and what kind of bond is holding the identical molecules of this compound together? So, this is one way of drawing a representation. This is something organic chemists love to do. Me too. I love organic chemistry. It has two pairs of electrons on it, so this is polar. So that means it's either going to be hydrogen bonding or dipole-dipole bonding. In order to understand which one it is, you look at the oxygen. Is there a hydrogen bonding to that oxygen? That electronegative oxygen? No. So it can't be hydrogen bonding. So the answer to this is indeed dipole-dipole bonding, as described by the people of the silly land of the Union. Okay? So, your assignment, again, this has been sent to you, is to find the polarity of this and tell me what bonds are holding them together when they're by themselves. Okay? Good luck.